Ben is going to depart a little bit, but he's been doing a lot in solar sailing. He's been interested in solar sails since reading Project Solar Sail and working in high school on a paper that describes the building and potential future of solar sails. He was awarded a bachelor's and master's in aeronautics and astronautics from the University of Washington, specializing dynamics and controls. And his master's thesis was on solar sail altitude control by shifting the center of mass. He's worked a couple of years at Lockheed Martin in Sunnyvale on spacecraft control systems using torque rods, reaction wheels, thrusters, and controlled momentum gyros. So Ben, thank you.
Mm-hmm. Right, thank you. I think the previous talk meshes nicely with, I think, what I'm going to be talking about maybe the lead up to that vector, to the position and velocity that gets you to the target star. So I've been working on the Near-Earth Asteroid Scout mission since last year on the attitude control system. So what I want to be doing is walking through aspects of the NEA Scout mission and then comparing that to aspects of the problem of sending a beam-propelled sail to another star or closer targets. So Near-Earth Asteroid Scout, its mission is to perform a slow flyby of a near-Earth asteroid. The spacecraft is about a 6U CubeSat with a 86 square meter sail that's about 30 feet on a side. And it's manifested to launch at the end of 2019 on the first launch of the SLS rocket. And we're planning on about up to a 2.5-year mission duration to do that. And the main purpose of it is to be able to fly in close proximity to an asteroid and then acquire enough information about it that they can use it. The purpose of it was to characterize an asteroid cheaply, efficiently with a solar sail so that you could then figure out if it's a target you wanted to send more assets to go explore. And by comparison, for beam propulsion missions, for truly interstellar missions, you're trying to get to another star and perform reconnaissance on the bodies in orbit there so that you can perhaps follow up with more in-depth missions. Or for precursor missions, you could perform reconnaissance of Kuiper Belt work cloud objects, or just fly to the interstellar boundary and examine the space environment, which is probably the least stressing case because you don't particularly care nearly as much what your trajectory is at that point. The entire mission is driven by the scientific objectives, which in the case of NEA Scout comes in 3 parts. There's within 50,000 kilometers, we start taking images of the asteroid to nail down exactly what its orbit is so that we can perform the close flyby. And that's done using some optical navigation and to determine its orbit and our relative orbit so we can hone in on it. And then as we get closer, within 100 kilometers, we can start getting some of the larger scale properties of that object, volume, shape, spin, and if there's any local environment, like if it has any moons or dust or anything around it. And then finally to perform a very close flyby and get higher resolution images of properties of like the surface composition, boulders, regolith, and so forth. Now, in the case of interstellar precursor missions, for precursor missions, what you'd want to do is sample the space environment, like the charged particles and fields as you transition from the environment around the sun to interstellar space. Or to perform like New Horizons style missions of more objects out in the Oort cloud and the Kuiper Belt. And then for interstellar, it'd be your mission might be similar to what NEA Scout's doing in that you're trying to characterize that target star and its planets and the star itself so you can follow up with more in-depth missions in the future. And then based on those requirements, like as the previous speaker discussed, you want a certain accuracy of distance away from your target so that you're actually able to take those pictures and learn something about your target. And then to do that, for NEA Scout, we basically want to have an accurate enough trajectory that we're able to get that close. So we have the luxury of actually correcting our trajectory continuously throughout the mission. And the chart over here is essentially showing the sail trajectory, and also the little red arrows are the thrust vectors that are produced by steering the sail at different angles so that you can get yourself all the way to the asteroid. And as we go, we communicate back with Earth, and we're able to do orbit determination to figure out where we actually flew to, and then correct any errors in that trajectory by changing how we steer the sail in the future, so we can hone in on it. Then finally, in the last month, as we approach the asteroid, we can take pictures of it and really hone it in so that we can get into, I think, probably within the kilometer level distance from the target. Now, unlike that, with beam propulsion, once you've fired the lasers as much as you can and have established your trajectory, it's going to be really difficult to try to correct it further. But in order to reduce those errors, when you first deploy the sail, you may want to illuminate it briefly so you can see how exactly your sail is responding to your beam. So you know that when the sail tilts to different angles with respect to the beam, what force and what torque does it produce? And then with that information, you can much more accurately predict what its trajectory is going to be. And that's actually something we're going to be doing continuously during the mission with NEA Scout. We're going to start using a model of the force and torque that we assume is true, but then we're going to correct it as we look at things like how our attitude control system responds to the solar torque and how the orbit changes in response to the solar force. So you could do that as well with an early calibration phase using beam propulsion. And then finally, you perform your beamed boost, and then you coast to your target, and hopefully accurately enough to perform your science mission. So there's a lot of uncertainties that can happen in this phase that you want to capture and make sure your system accounts for, and try to tighten those down as much as possible. And in the case of a precursor mission, you don't have to go as far. You may have a lot better knowledge of your targets. Like you may have certain good knowledge of, say, a Kuiper Belt object's orbit, so that you could target it more, know that where it is. And you also don't have as far to go, so you're not going to go as far, of course. And then the space environment type missions, where you're just sampling the solar wind environment out at a long distance from the sun, it really doesn't matter that much where your trajectory is going. Now, in order to get the trajectory and the guidance nailed down for NEA Scout, we needed a model of the forces and torques on our sail. And to do this, from the mechanical design of the sail, NASA Langley performed finite element modeling of it to get a prediction of what the real shape of the sail is. And then using all 64,000 of these little triangles in this model, we reduced that down into a tensor-based force and torque model called the generalized sail model that tells you, basically it's an equation. Instead of like this gigantic model here, you have a simple equation that tells you what the acceleration of your sail is going to be, or what its torque is going to be at different attitudes with respect to the sun. And we've also performed optical testing to get a sense of what the specular versus diffuse reflection is on the sail, because that can have a big effect on the torque. Because if you start getting force vectors from the solar force acting in the plane of the sail, that can torque around the center of mass and cause it to turn. And what we found from this process is that this chart on the left is a comparison between a flat plate sail that has optical properties versus this model with the shape. And it's actually, a flat plate is a very good approximation for NEA Scout because it is a relatively flat sail. This model here is exaggerated. But it turns out that there's a big difference in the torque. So these subtle variations in the shape, they essentially act like little vanes that torque the sail. So we want a good idea of what's going on here. So we intend to have a calibration phase just for the torques. So we're just going to point the sail at different attitudes and observe how our attitude control system responds, and then work out what our actual torque model is based on that. So in the case of a beamed sail, I think previous speakers have gone into greater depth on this, but the force and the torque are going to be a function of properties of the beam and properties of the sail. There's going to be the power and the distribution of the beam, and if there's any variations in this, variations in the beam attitude, that's going to affect your forces and torques. And then the sail itself, the shape, its optical properties, and how it's oriented relative to the beam, and also its position within the beam. All of these are going to go into this model of the torques and the forces, and are going to cause the sail to either point off of the beam or drift against the beam. And you want to make sure that, given all the uncertainties in all of these parameters of the beam and the sail, that you can keep it where you want it to be and how you want it to point, what direction you want it to point. Because as you drift off the center, your forces are going to drop as the beam intensity is less of the light hits it. Even if it's stable, if it starts oscillating from side to side, it's basically going to be shedding force, and you're not going to accelerate as much as you wanted to. And then for the attitude, dynamics, and control, on NEA Scout, we have an active control system because our sail is, due to the constraints on the very small size of the spacecraft bus, we're not able to make it passively stable. So it's actually an unstable sail. So we have a combination of sensors and actuators that keeps it pointed where we need it to. We have a star tracker that gives us a inertial attitude with respect to the surrounding star field. We have sun sensors. They're essentially mostly used for emergency backup. We have gyros that tell us what our rates are. And we have our primary actuators are actually reaction wheels. So we can spin these up to slew and point our spacecraft where we need it to. But over time, the solar torque is going to spin these wheels up until they hit the limits of their bearings. So to do that, to control that, we actually control the solar torque on the sail by shifting the center of mass using a device that's located that splits the spacecraft bus in half. So we can actually move our center of mass around, manage the solar torque, and keep the wheel speeds under control. And we also additionally have a cold gas RCS system that's used not as a primary actuator, but as a backup, and also for when we initially detumble off the rocket. And it turns out this mass translator can only manage 2 out of 3 of the axes. So there's a small, what you might call a windmill torque in the surface of the sail that causes the sail to spin around like this. And then, so we can use a little bit of RCS to keep that under control. And there's other strategies we can use. We can actually rotate the sail to trim that out. But we designed this entire system and its corresponding software to let us keep the sail's attitude pointed where we need it to throughout the mission so that we can follow the trajectory we need. Now, additionally, we've been working with the University of Maryland to develop some reflective control devices so that we can manage the solar torque without any moving parts. Okay. So the reflective control devices, these are some thin film LCD screens where if you subject it to, I believe, an electric field, you can get the particles to line up so that the light will go through it. Otherwise, it is diffuse. So you can essentially mount these along the edges of a sail, and if you turn them on, you'll let the light go through so that the light will be hitting stronger on the opposite side and induce a torque on the vehicle. So this is a way to do active attitude control without any moving parts. These were first flight tested actually on Japan's Ikaros solar sail, and we're developing our own here, and with the intent of using them on future sails. Now, in the case of beam propulsion, now primarily people have talked about doing passive stability, so that you can look at a variety of different sail shapes and configurations that attempt to just automatically keep the sail centered on the beam and pointed in the right direction so that it thrusts where you need to. Now, it might be worth considering looking at active control. This is going to require sensors on board to determine where you're pointed relative to the beam or inertial space. And in terms of actuators, one could consider reflectivity control devices, changing the shape, which is essentially like having steering vanes, or shifting the center of mass so that you keep it on there. Now, I think maybe one primary reason to look at active control is because you may want to thrust in a direction that's not aligned with the beam. Now, due to constraints of where your beams are located, I mean, they're a moving target because of the orbit of the Earth. You're a moving target because of your orbit. You might actually want to, at times, produce a thrust that goes off of the beam. And to do that, you'd need to maintain an attitude of the sail that's not aligned purely with the beam. And it might be required to work out with the complexities of the orbit dynamics of where you want to go and where your beam is, where you are. So it might open up the trade space because you might be severely limited in when you need to shoot the laser at the sail. So it's something to consider. In conclusion, for NEA Scout, we did a complete mission design where we went, we've built most of this. It's going to be integrated and tested through next year. So complete mission design, starting with the science objectives and working out the trajectory, navigation, attitude dynamics, control, and then testing out a variety of uncertainties to make sure that the sail is robust because we're not going to get exactly the shape of the sail we anticipated, orbit determination is only so accurate. So we want to make sure all that's accounted for. Probably the biggest difference is we can correct all the way to the asteroid. We can correct our trajectory. Whereas with beam propulsion, you've basically got whenever it is you're firing it, and that's it. And the trajectory requirements are a lot more stringent because the target you're aiming for, you require much, much greater accuracy. Like I said, there's only a few opportunities to change that trajectory. So it's very critical to understand all the uncertainties and reduce them as much as possible. You might consider active attitude control if passive stability is not sufficient. And I think it's probably pretty critical to calibrate your beam and your sail after launch and deployment of the sails. You know what the system is you've got before you ever before you fire up the beam and propel it out of the solar system. And if you did more than one boost, if you could do more than one boost phase, that would allow you to close the loop and correct some uncertainties from the first one. Although I realize you're going to need to probably aim your lasers a lot farther away for a follow-on phase. And to test out the beam propulsion technology, a much easier mission is to do a solar physics one, because you don't particularly care what the final trajectory is, just so long as you get there in a reasonable amount of time. And for the next steps, I think the approach we've taken with NEA Scout could be applied. In the case of the trajectory, you've already worked out that analysis to some extent. I would build a whole attitude controller in the loop with the beam pushing on it. And then the office I work in is all about Monte Carlo analyses. So we can throw in lots of variations on every aspect and see if we can see what it takes to keep the beam painted on the laser and see if your trajectories get you where you need to go. And then work backwards to see what level of uncertainty can we tolerate and still meet the ultimate objectives of the mission. And then if we go and look at our technology, we might realize we're not able to do that in a lot of cases. So then what do we need to focus on in terms of advancing our state-of-the-art in all these things? Like, I imagine the orbit determination, the initial orbit determination's got to be really, really good so that you can hit the sail. But I think working on NEA Scout, there was a lot of lessons in that process that could be applied to this problem as well.
I'll start off. Have you looked into what you might expect to see in terms of transitioning between low energy transfers to actually explore the solar system?
Low energy transfers, you mean like going through Lagrange points and following those?
Oh, you might indeed investigate SCO1. You might indeed do that, but you could you basically have a low reaction mass system of maneuvering, and so to have planetary missions controlled in some sense by AIs on Earth, but you could have a solar system investigation system going on. And I wonder if you've looked at it, or NASA's looked at it. Have you worked out their trajectories?
Well, I think, are you thinking like in terms of gravity assist and so forth? Because I think, we're doing some of that here. We're doing a bunch of gravity assists. We're doing like 3 gravity assists on the moon before we ever leave Earth-Moon space to head to the asteroid. And we've looked at some potential follow-on missions where we regularly revisit Earth to help do inclination changes to get to some more aggressive asteroid targets.
I'm very interested in what you're planning to do with your electro-optic diffuser. I know JAXA Icarus had a very small demonstration with their diffuser. I think they got maybe about a few milliradians of attitude change, and then they stopped.
Oh.
So yeah, it sounds like you guys could be a little bit more aggressive. Can you talk about how much attitude change you expect to get out of that, and the thickness, what it adds to the aerial density? Thanks.
The thicknesses we looked at were probably starting from as thin as our sail material going on up to, I don't know, 10, 20, 50 microns. And we did some trade studies where we were essentially sizing and locating these panels out at the corners and edges of the sail big enough to more than account for all the solar torque. Because the intent was to continue using a reaction wheels for steering and then use these devices to keep them under control the entire time. So it would accommodate all of the solar torques we would expect to see on the sail over the life of the mission. So that's, unfortunately, I'm forgetting the magnitude of those torques, but you know. Yeah, it's like which power of negative 10 are we at? It gets to matter at this point. Yeah. Mm-hmm.
Hi, is the craft attitude control system principally autonomously regulated, or is it remotely operated? And if the latter, do you have bandwidth and assurance requirements?
Yeah, our control system in terms of following a commanded attitude, that's autonomous. We generate what attitude we want on the ground, and then we upload a time history, so it might have a week's worth of attitude commands to follow. But then the control system will autonomously steer the sail to go to that attitude, because it's using a star tracker to see very accurately where we're pointed relative to the background stars.
Okay, very nice presentation, thanks. I'm Greg Matloff, and a few years ago with Les Johnson, probably here and later in JBIS, we did a little study of the possibility of throwing NEA Scout out of the solar system as an interstellar precursor after its primary mission, assuming that goes well. Are you giving any thought to that possibility at this point?
Yeah, so there's two things that limit the life of NEA Scout.
Yeah.
One is that it's made from CubeSat parts.
One is what?
CubeSat parts.
Okay.
So we've planned for a 2.5-year mission, and
Yeah.
you know, we're crossing our fingers. The other is we do have a cold gas RCS system. What may happen is that if we run out of that gas, we have one reason we want it for the entire mission is because the mass shifting device will only control 2 out of the 3 body axes of momentum of solar torque. For the third one, we can use the cold gas, but it turns out if we tilt the sail to maybe about 20 degrees angle to the sun, we can actually trim out that third axis of torque just by rolling the sail to different attitudes. So long as if we had an extended mission, we'd probably have to always sail at a 20 degree or more angle to the sun.
That would be hard to do in interstellar mission with. Okay.
Yeah, I think at some point, yeah.
Thank you.
Yep. Right. Thank you.